In our last module, we were looking at the numerical solutions of Fourier transforms, and we used those numerical solutions of Fourier transforms as a tool to explore data. We looked at data from sunspot data to the damp-driven pendulum data. In this next module, we're going to look at the numerical simulation of random processes. So in physics, there are lots of examples of random processes. There's lots of problems that involve random processes that range widely from things like radioactivity to things like magnetization. So we're going to learn how to simulate, learn how to model such random processes. And at the heart of simulations or models of such random processes is the capability to generate random numbers. Specifically, in today's class, I want to look at building our own random number generator in which we're going to generate streams of random numbers. It's a random number generator that's based on simple arithmetic, multiplication, addition, division. It's a random number generator that we'll see has problems, has flaws, but it will be an introduction to generating random numbers on a computer. So in physics, there are processes that are truly random, and there are processes that are seemingly random. And we're interested in both. We're interested in modeling both. We're interested in simulating both. So just as an example of something that's truly random, radioactive decay is truly random. It's impossible to predict the time of the decay of a radioactive nucleus. The laws of physics, the laws of quantum mechanics don't allow you to predict the time of decay of a radioactive nucleus. You can only predict the probability of decay of a radioactive nucleus. So that's an example of something that's truly random. On the other hand, the motion of a dust particle in the atmosphere, that's called Brownian motion of the dust particle in the atmosphere. That's a process that's seemingly random. In principle, if we knew the positions of all the molecules in the atmosphere and the velocities of all the molecules of the atmosphere, we could calculate all the collisions of the dust particle with all the molecules in the atmosphere and determine the path of the dust particle in the atmosphere. It's just that it's obviously completely impractical to know the positions and velocities of all the molecules in the atmosphere to carry out that calculation. So in the case of the dust particle in the atmosphere and its Brownian motion, that's a process that we would call seemingly random. So to simulate either the truly random or the seemingly random process in physics, we're going to need to be able to generate random numbers. This is the heart of the modeling simulation of random processes. I should say that there's plenty of other reasons beyond physics for generating random numbers. Big examples are, for example, security, encryption. That's a case where the generation of random numbers is very important, very critical. Other examples are, for example, gaming and gambling and lotteries. That's another case where the generation of random numbers is very important. But we're going to confine ourselves to this physics world of modeling and of simulations. So when I think of a single random number, I think that that's a number that is drawn from some set of possible random numbers with some equal probability for each of those possible random numbers. So that would be a single random number. For example, if I roll a dice and I get a result from rolling the dice, that's a number that is drawn from a set of numbers, a set of 6 numbers. So we've drawn one number from a set of 6 numbers. Now, actually, if you just look at a single random number, it's hard to assess whether that's truly a random number or was not a random number. To assess whether a random number is truly a random number or not a random number, we have to look at sequences or streams of random numbers. And actually in modeling and simulating, we're typically using large streams of random numbers. And so when you have large streams of random numbers, you can ask the question, you can address the question whether particular random numbers are independent of the other random numbers, for example, and assess whether your stream of random numbers has randomness. Now, we're going to be talking about computer-generated random numbers. So at first sight, it seems a little crazy to ask the computer to generate random numbers. So computers are devices that follow the instructions that they're told. Computers are not devices that operate by chance. And so how do we make random numbers in a computer? In fact, it seems a bit reckless, perverse to ask a computer to make random numbers. Well, there's 2 terms that you'll see in association with random numbers in computers. One term is pseudo-random number generators. Here it is. And the other term is true random number generators. So pseudo-random number generators, they use a mathematical equation to generate the sequence of random numbers. And pseudo-random number generators are not truly random. We just ask pseudo-random number generators to appear to be random. On the other hand, truly random numbers, here we are, these use some physical phenomena to generate the random numbers, and they can be truly random numbers. So one characteristic of pseudo-random numbers is that the sequence of pseudo-random numbers will sooner or later repeat. A characteristic of truly random numbers is that the sequence of random numbers is aperiodic. It doesn't repeat. Now, in modeling, in simulations, we're typically using pseudo-random numbers rather than truly random numbers because it's much more convenient and because they're sufficient for carrying out simulations. They're sufficient for carrying out modeling. In today's class, we're going to explore what's called a linear congruential pseudo-random number generator. In the next class, we're going to use, from the NumPy library, a Mersenne twistor pseudo-random number generator. Now, the one we're going to work with in today's class is based on a simple mathematical equation, a simple bit of arithmetic, the simple use of multiplication, division, and addition to generate a sequence of random numbers. And so we're going to explore that. The one that we're going to use in the next class from the NumPy library, that doesn't use an arithmetic equation to generate the random numbers. It doesn't use traditional multiplication, division, and addition. Rather, it uses things like shifting bits, like performing ORs of bits, like performing ANDs of bits to generate the sequence of random numbers. So this slide outlines the linear congruential random number generator, LCG for short. So the equation describes how the generator works. The equation tells us how the generator works. So if you look in the equation, there's a quantity x subscript n. X subscript n is the sequence of random numbers we're going to generate. So we'll start with an x naught, and then we'll calculate an x1, calculate an x2, calculate an x3, and so on and so forth. So the equation is telling us how to calculate the stream of random numbers from a starting or seed number. So specifically, that equation is telling us how to calculate x subscript n plus 1 from x subscript n. So once we know one random number, say x1, we can calculate x2. Once we know x2, we can calculate x3 in this recursion relation. And so that's how we calculate the stream of random numbers. We calculate the stream of random numbers by a simple calculation that has a linear piece to it and a congruential piece to it. So the linear piece is over here on the left-hand side, and the congruential piece is over here on the right-hand side. And these two pieces together involve the arithmetic of multiplication and addition and division. So the equation says that to calculate x n plus 1 from x n, you multiply the prior random number by a constant a, you add to that a constant c, and then you find the remainder from division by this constant m. And so that's the procedure involving multiplication, addition, and division to find our random numbers. And so that's how we're going to try and generate a sequence, a set of random numbers. So there are three parameters in this formula or equation that are associated with the LC random number generator. So there's the multiplier, that's the A. There's the constant, that's the C. And then there's the divider, that's the M. And so when you run this random number generator, when you use this random number generator, you're using it with values for M, A, and C. Now, a couple of points. To start the random number generator, to start generating a sequence of random numbers, you've got to have an initial seed, x naught. So that's an initial integer seed, x naught. Once you've got that seed, you can calculate a stream of numbers from the random number generator, and it's calculated completely deterministically. So if you know M, C, and A, and you know your seed value, you know you can calculate this stream. I could calculate this stream. Anybody could calculate the same stream of random numbers based on the three parameters of the random number generator and the particular seed that we've chosen. It's actually quite useful in modeling and in simulating of physics problems to be able to generate the same stream of random numbers multiple times. If you're testing your program, if you're debugging your program that's doing this simulation or doing this modeling, it's useful to be able to generate the same sequence of random numbers. And you can generate the same sequence of random numbers by just using the same seed. If you want a different set of random numbers, if you want a different, stream of random numbers, then change the seed. But if you want the same random number sequence, then keep the same seed. Couple of other points about the equation. The possible range of random numbers is determined by m. So we take the remainder after division by the integer m. And so the remainder can run from 0, that would be the smallest remainder, to m less 1. That would be the largest largest remainder. So M determines the range of numbers. So if M, for example, was 32, then the range of integers that you could generate with that random number generated with M equals 32 would be from 0 to 31. There would be at most a sequence of 31 random numbers before the sequence of random numbers starts repeating. If M was 128, then the possible random numbers, possible random integers are from 0 to 127. So in that case, the greatest, the largest period sequence of random numbers before you start repeating is 128 different numbers from 0 to 127. Now, for M equals 32, getting a sequence of 32 different numbers, that's the biggest period you can get. For M equals 128, getting a sequence of 128 different numbers, that's the fullest period that you can get. Often the problem with this type of random number generator is that you don't get the full period. You don't get the full set of random numbers. And that's an example of a flaw in this type of random number generator, where it doesn't meet the test of randomness. Now, avoiding that flaw or minimizing that flaw comes down to your choices about the two other parameters. You've got two other parameters. You've got the multiply A and you've got the additive constant C. And so for different values of A and C, we'll discover that you get different periods. So one set of A and C might give a short period, another set of A and C would give a longer period. You also get other problems or avoid other problems with the choice of A and C. For example, you can get patterns. You can get iterative patterns or sequential patterns in consecutive random numbers by poor choices of A and C. So we're going to look when we explore this random number generator, using this random number generator, we're going to look at a bunch of examples of M's, A's, and C's to see the pitfalls, to explore the pitfalls, to explore the flaws, and to examine the randomness of this particular random number generator.